Okay, I mentioned this idea in passing on Monday, but I want to examine more closely the idea of a derivative as a function. We were writing f prime of a. Given our function f of x, we wrote f prime of a as this limit as h went to 0. But a here is a particular x value. If I leave this in x, then I would write this exact same definition all in x. See exact, I just changed the a back to an x. And then I think about what's going on here, and I say to myself, that's a function. This is a function of x. We started with our f of x. We took its derivative. This derived function is a brand new function. Wait a minute. A function assigns a value to each x value. That's the definition of a function. You put a value in, you get one and only one value out. Each value that comes in, you get one value out. What value is f prime assigning to each x? What is this, or even this, what does this expression represent at the point A? My instantaneous rate of change, which on a graph represents slope of a tangent line. For the application, it will depend on what our application is. On a graph, it represents slope of a tangent line. Okay, well, if that's our assignment, let's take a picture. Here is a graph f of x. I have no freaking clue what the equation for this graph is. None whatsoever. Yet I can still take this graph and estimate f prime as I move from left to right across this graph. Because I'm going to think of creating a new picture, f prime, by going point by point. Well, roughly point by point, and looking at tangent lines. So let's think about all the way on the left edge over here. If I drew a tangent line to this curve, let's say at this x value, there's my x value a. What would you get for a slope of a tangent line at that spot? It's negative something, right? My tangent line is going to be going this way. That might be -1, -2, -1.5. I have no idea because I didn't put a scale on this, but it'll definitely be a negative number. So down here, I'll get a negative number. This y value is the slope at this given x value. Let's move a little further. And what happens at 0? Right here. If I drew a tangent line there, what would you be able to tell me about the slope of that new tangent line? Less negative, but still negative, right? It should be maybe a little shallower, but that makes it less negative. That means we're going to be closer to the x-axis, aren't we? We're going to have a little less negative a value. Here, B. As I keep moving over, what happens? Well, I'm sure it's positive over here, right? What happens between negative and positive? I should have a 0 somewhere. The intermediate value theorem, right? So I might get that here and maybe this point C. It'll be a positive number. But then what happens when I get here? It might be 0 again. And then what's going on this section? It goes back to negative, and then, so I'm going to have a curve. Yeah, I even managed to draw something incorrect. I was moving too quickly. Between D and E, these slopes should be negative. But they should get less negative, then more negative, then less negative again. So I would expect to go like that. Just like here I went, and then I would get positive slopes. This is my f prime of x. I don't have a single equation involved here, but I can still draw a picture. I can estimate, approximate, what I think the graph of f of x looks like. Page 154. They actually do calculate some values here every now and then. They actually draw a slope and say, well, that's about negative 2/3. So we should be at a y value of negative 2/3 here. We see this coming down, going up, coming down. So negative, positive, negative. This visual interpretation allows me to think about derivatives without actually evaluating them. Grab your graphing calculator. I believe we did this example on Monday, yes? 2x minus x cubed. I'm just going to graph this for the moment. Standard window, minus 10 to 10, minus 10 to 10. Well, there's not much going on out here to the left and out here to the right. So let me change this window a little. So I can see more of what's going on in the x's. Okay. I want you to do for this graph what we just did on paper. What would you expect to see in terms of our derivatives values as we go from left to right across this picture? Over here on the left, what do I know about the slopes? And then way over there on the right, and in the middle, there's a piece where it's positive. So I should go from negative to positive to negative. I can actually have my calculator directly calculate the derivative. Now, it depends on which version of the software your calculator has as to what this next step looks like. I'm going to tell it in y2 to take the derivative of the thing in y1. Under the math option, math button is over here on the left. That little arrow says there's more down. So I'm going to go down. And option number 8 says numerical derivative. My calculator doesn't know how to do this stuff formulaically. It's not a computer algebra system. That's why we couldn't use calculators that said CAS. It's going to calculate the derivative value at each dot using little limits over and over, and then it's going to plot that dot. So I hit enter here on number 8. If you don't see this, if you see the word n derivative or n deriv, come talk to me at the end of class because you have an older version of software. I want to tell it to do the derivative. That ddx, well, dd whatever, means do the derivative. I need to put the variable we're using down here. That's why that's blinking. It's even blinking with a little a, so I can just type our x value. Then I need to tell it which equation to use. I could retype this equation if you want. But I also tell it, hey, use the thing in y1. Under this variables button right here are a list of all the y variables. Functions. I want to use y1. I hit enter again. It now knows I want to take the derivative thing in y1. This vertical bar is where do I do this? I'm taking the derivative, that's what the ddx means, of the thing in the parentheses, where? I want to do it for every x value. So in that last little box, I'm going to hit x again. And then I hit enter. If I go back to the graph, it will draw the equation of my derivative. And we see negative values, positive values, negative values. Exactly what we expected to see. I like this. If you've got the color version of the calculator, there'll be 2 different colors. That's helpful. I have the older black and white version. That's fine. but there's my original function, and there's its derivative. We did this one on Monday. We actually worked out the derivative, didn't we? What did we get? I was going to say, I got to look at the orientation. If my function is 2x minus x cubed, then we showed the other day that my derivative is 2 minus 3x squared. Okay, wait a minute. Wait a second. 2 minus 3x squared. That's a quadratic equation, right? What's the graph of every quadratic equation? They all have the same shape. Say again? A parabola. And it's got a minus 3 with the x squared. That means it should be going down. Isn't that what our graph looks like? Hot damn. Now, the calculator notation, a short diversion into notation. I keep writing f prime of x. And this notation for my derivative was created by Pierre Fermat. Isaac Newton used f dot of x. If I write y equals f of x, you'll often see y dot or y prime. Same idea. They all mean a derivative. But we can also use this other notation. I ate my piece of paper. Here it is. The derivative with respect to x, because I'm looking at change in x, right? Change in y over change in x. I could say, oh, I want to do dy dx, or d dx of y, or even d dx of f, or whatever thing I'm looking at. These notations were made popular by Gottfried Leibniz in Germany at the same time as Newton was working on this in England. Later mathematicians would use what's known as operator notation. So you will sometimes see d of f. Or if we want to make the emphasis on the fact that we're doing change with respect to x, you might see dx, like that. All of these mean the same thing. But when you've got these parentheses, like Fermat and Newton, then you can plug in fairly easily. So if I want to plug in a value, say a, I could go, oh, well, I want f prime at a, or f dot at a, or even y prime of a. But where do I do that here? I can't. That's what that vertical bar is for. So when I write dy dx at a, that's the same idea as this. Sometimes, as we saw in the calculator, people will write x equals n. If there's only one variable for me to plug into, I usually don't write x equals, but that's where the calculator got it from. The same thing happens with our operator notation. Can be written like this or like that. I will not use operator notation very much this semester, but we do see it later in some of our other courses. Questions? Leibniz's notation was actually fairly controversial for quite some time, because what he was really saying is that we're dealing with little bitty changes as slopes, right? And when Newton brought this idea up, that these little bitty changes that were so small they effectively vanished, but left an effect upon a function, his derived quantity f dot Newton called that a fluxion. It's a weird ass name. But Newton, when he presented this paper, said this is what is left behind as the effect of F as these little changes vanish. Archbishop of Canterbury, Bishop Berkeley, looked Newton in the face and said, "Are you telling me that the ghosts of departed quantities have impact upon the world? Are you sure you wish to commit this heresy of consorting with ghosts, sir? Congratulations, welcome to the Catholic perspective on calculus. You are all heretics. We're consorting with ghosts." Needless to say, Newton got in trouble with the Church of England. Leibniz was German, he didn't care. So his notation really said, yeah, these are vanishing things, we're going to use them. Berkeley would get told off later by other members of the church, and Newton would be fine because it worked really well. Let's try another one. Now, I did say that one of the biggest problems we're going to have in doing our derivatives is the algebra involved. So I want to do the derivative of this function, and the method I have to do it to find f prime of x is to do the limit as h goes to 0 of our difference quotient, f of x plus h minus f of x over h. So that means everywhere in here that I see f of x, I need to replace that x with an x plus h. Mother. Well, that certainly qualifies as unpretty. I'm subtracting two fractions. What do I need to do to subtract two fractions? I need a common denominator. So I'm going to multiply this fraction by this denominator on top and on bottom. I'm going to multiply the right fraction by the left denominator, top and bottom. So I have 1 minus parentheses x plus h over 2 plus parentheses x plus h times 2 plus x over 2 plus x minus 1 minus x over 2 plus x times 2 plus x minus h over 2 plus x minus h. Bleh. That's gross. All right, wait a second. The bottom of these fractions is the same. So I'm going to get 2 plus x plus h times 2 plus x on the bottom. Up here, I'm going to get 1 minus x. I'm going to multiply this out. Minus h times 2 plus x minus 1 minus x times 2 plus x plus h. That's all over an h, and there's still this limit as h goes to 0 in front. Whew. I need you to take this very top part and multiply it all out. Leave these two alone. Just worry about the very top line there, and let's do the multiplying out. When I multiply these pieces, I'll get 6 things. When I multiply these pieces, I'll get 6 things. Yuck. But some really nice things happen. What really nice things happen? I get a lot of canceling. What actually cancels? My XH cancels, minus XH, minus another minus XH. Those are gone. What else? Minus X squared, minus X squared. Yeah, those are gone. The 1x here and the 1x there, they're going to cancel. And so are the minus 2x here and the minus 2x there. What else? The only things that survive on that top are a minus 2h and then minus another h, which gives me a total of minus 3 of them, right? 2 from the beginning and 1 from the end. So I have minus 3h over 2 plus x plus h times 2 plus x. And then I have this h on the bottom, which I'm going to rip out and flip over. I hate fractions within fractions. So I pull it out of the bottom and flip it over. What happens here? One more time, I get to cancel again. My h on top will cancel with this h on the bottom. And once those are gone, then the only h I have is right here. So what happens as h goes to 0? This piece is gone, this little h right here, and that makes the thing in the left parentheses 2 plus x. Wait a minute, that's the same thing on the bottom twice, isn't it? Now, here's the fun part. What was my original equation? The original f of x we did? Please notice that function has a vertical asymptote in it at x equals -2. That's where the bottom's undefined. Here comes my derivative. This graph, my original f of x, as I go from left to right, is always decreasing. It's always going down. My tangent lines are always negative. This is always negative. There's my derivative. It's always below the x-axis. And what's more, where is this undefined? Exactly the same place our original function was undefined, isn't it? Huh. If I have a function and I have a place where that function is broken, I can't take a tangent line there. If I don't have a tangent line there, I can't possibly have a derivative there. Every place my function is broken, I lose my ability to take a derivative. Now remember, our definition of f prime is a limit. But that asymptote is the place where my function isn't continuous. Continuous was a three-pronged thing, right? We had to have a limit, we had to have a value, and they had to match. Differentiability, being differentiable, requires a little bit more than being continuous. It requires not just f and the limit as we approach on f, but the tangent line. So there's more added. Being differentiable is a stronger idea than just being continuous. As a matter of fact, it turns out that there's this really nice result. If f of x is differentiable at a point, then f of x is continuous at that same point. So wherever you have derivatives, you automatically get continuity, but not the other way around. Having a function that is continuous doesn't mean it will be differentiable. Okay, as soon as I say something like that, the geek in the back of my brain goes, right, sure, show me. I don't believe you. That's an if statement. If you're telling me it won't work the other way, you should be able to give me a counterexample. Tell me, what do you know about this function? But more, what's its graph look like? That's a V shape. if I want to look at this one, this is definitely continuous, right? It's continuous. It's a straight line on the right. It's a straight line on the left. And as we go to zero from each side, we go into, as x goes to zero, the y values are both going to zero. So this is continuous everywhere. But what if I look for a derivative? If I drew a tangent line anywhere over here on the right, that tangent line would be the exact same straight line as that piece of the curve, wouldn't it? And if I drew a tangent line over here on the left, the tangent line would be the exact same line as that side of the curve. What about at zero? If I try and take a tangent line and I approach from the right side, I should be going in a positive direction. If I approach from the left side, I should be going in a negative direction. As a matter of fact, if we write out our derivative, we'll have to do it from each side because this function is defined in two pieces. So I would have to do a left limit and a right limit to do f prime of x. I'm sorry, f prime of 0. F of 0 plus h minus f of 0 over 0 over h, sorry. But I'm going to cheat. And I'm going to tell you we did this limit. We did this in our looking at left limits and right limits. And from the left, this is -1. And from the right, this is 1. This limit doesn't exist. If I have a different limit from the left as I do from the right, then I don't have a value. So f prime of 0 doesn't exist. Here's a function that is continuous, but it's not differentiable at 0. And if I look back at the graph, the thing that I see in the graph that alerts me to this being an f up is that corner. Whenever I see a sharp corner like that, I have a problem. On page 159, we see a sharp corner. And because we are taking a limit, I'm going to zoom in on that sharp corner. No matter how close I zoom in, I'm always going to get one side where the tangent line is going in one direction and another side where the tangent line is going in a different direction. But if I have a derivative, as I zoom in, it looks more and more and more just like a straight line, doesn't it? This corner is the problem. So whenever I have a corner, I have a problem with my derivative. A derivative is representing a slope, right? So let me ask you this question. What other types of problems can I have when I look at the slope of a tangent line? What kind of lines mess up slopes? The hell do you mean mess up slope? What kind of lines don't have a slope? A horizontal line has a slope of 0, but a vertical line doesn't have a slope. So if I had a place where my tangent line went straight up and down, I'd be in trouble, wouldn't I? If I have a corner, I have a problem. If I have a place where my graph is vertical, I have a problem. If I have a place where my graph isn't continuous, I have a problem. So here are 3 conditions that mess up having a derivative. If you have a corner, a jump, an asymptote, a discontinuity, or a vertical tangent line, you can't have a derivative. And all three of those can be determined by looking at the picture. If it's differentiable, then it must be continuous. If it's not continuous, it can't be differentiable. But by the way, is an example of a statement and it's contrapositive. Questions? Let me back up to our previous example. Here's our 2x minus x cubed. And its derivative, 2 minus 3x squared, right? I'm going to turn this function off. I go over and highlight over the equal sign. I hit enter. See how it's not lit up anymore? That means it's only going to graph the derivative. It's not going to graph the original function. So here is our parabola that we know to be our derivative. And we worked out what this function was. But now, imagine that's not in the picture anymore. I have a function. Let's take its derivative. I have this function. What do we know about slopes of tangent lines? If I drew the derivative on here, what would we expect to see? Something that was positive, followed by something that was negative, with a 0 in the middle, right? So I should have something that goes positive to negative. I can take this expression and repeat it down here. Math, option number 8, take the derivative with respect to x of the thing in y2 at x. So that's asking me to take the derivative of the derivative. And if I do that, I see exactly something that, well, eventually, it's thinking. See that little line up there in the corner moving up and down? That's its little version of the spinning blue beach ball that we see on the MacBook. I'm thinking, I'm getting there. It starts positive, it goes to negative. It does what I want. But if I am taking the derivative of a derivative, I should get f double prime of x, a second derivative. But how do I get there? Limit as h goes to 0 of what? Well, of f prime x plus h minus f prime of x over h, because I'm taking the derivative of the derivative. But I know this expression. And again, now it's just a matter of algebra. I'm going to multiply out that x plus h squared. X squared plus 2xh plus h squared minus 2 minus 3x squared. And again, I'm going to multiply out the 3 here, and I'm going to see what nice things happen. 2 minus 3x squared minus 6xh minus 3h squared minus 2 minus 3x squared. Don't forget all of the parentheses that are involved there, over h. And then I see some lovely canceling. My 2's cancel, my 3x squareds cancel. These two pieces in the top survive. Minus 6xh minus 3h squared. But that's all over h. So I can cancel the h on the bottom with one of the h's in each piece on the top. What happens as h goes to 0? Mumble, mumble. The 3h is gone. Poof. This is my second derivative. This is f double prime of x. It's the second derivative of the original equation. It's also the equation of a straight line, isn't it? And isn't that the graph of a straight line? By the way, if I use the other notation, we had the first derivative, and now I am taking the derivative of that, right? Please notice the top, there are two d's, right? It's a d and then another d. So we will write this as d squared. The bottom is two dx's. So we'll write dx squared. That is the second derivative of f with respect to x twice. I can do it more than once. I could do a third derivative. Third derivative of f with respect to x 3 times running. Or I could do, f triple prime. After a while, I run out of primes and it gets hard to keep track of up there. So once you get about through 4, people start using lowercase Roman numerals for a fourth derivative. I personally get really unhappy about this notation, which is why I tend to use this one, because then I'm just using regular numbers. But you can do as many derivatives as you want, and they're all useful in different places. Most of the time, I won't go much beyond the second derivative or third derivative for applications I'm doing. Statistics. Second derivative is related to skew. Third derivative to kurtosis. Physics. Second derivative is acceleration. Third is change in acceleration. It's also related to axial precession for our third derivative. And our second derivative is related to moments of inertia and rotation. There are applications all over the place. However, this is a pain in the ass. And if I'm going to spend the entire rest of the semester working on calculus and doing derivatives, I need an easier way to do this. Guess what we're doing tomorrow? But I would point out to you 2 other things. That's tomorrow. That's Friday. See that? That's a week from today. The review sheet is already up there. Please look at it and bring questions on Friday. I will see you all tomorrow for our shortcut versions.